Hey guys, today we're going to be talking about mutually exclusive or inclusive probabilities. So, what do I mean by inclusive or mutually exclusive? Uh, Real quick nuts and bolts, it's basically whether or not two events can happen at the same time. Okay, so if two events could happen at the same time, for instance, if you pick a card out of a standard deck of cards and it's a numbered card, and it's a red card. Okay, those two events, numbered cards and red cards, they overlap because I can pick one card out of there that satisfies both of those criteria. Okay, or another example here is if you have people living in the Eastern time zone, like all of us here in Georgia do. Okay, but that also includes people up in New York and Philadelphia, Canada, or at least a part of it. So there's a lot of places in the world that satisfy this Eastern time zone. But we could also say, hey, people that live below the Mason-Dixon line, if you're familiar with Civil War, little trivia, the Mason-Dixon line was basically the thing that separates the North from the South in terms of the United States. Okay. Now, there are people that live both in the Eastern time zone and below the Mason-Dixon line, like we do here in Georgia. Okay. However, there's people like up in New York that they are in the Eastern time zone, but they do not live below the Mason-Dixon line. Okay, so they're not the same sets, but there is an intersection. Okay, and specifically that intersection is non-empty. Okay, now mutually exclusive is when things cannot occur at the same time. One thing that I want to say real quickly is complements of sets or complements of events do qualify as mutually exclusive events, right? If you're in a circle, right, versus out of a circle, there is by definition no intersection. However, just because all complements are mutually exclusive to one another, that does not mean that all sets of mutually exclusive events are complements of one another. Okay, so I don't want us to get confused by making that assumption. All mutually exclusive means is that I've got two events that cannot occur at the same time. Okay, even though in a Venn diagram we might overlap the circles like this, what we're saying is this intersection here has a quantity inside it of zero. It's the empty set, right? If A is intersecting B and that's equal to our empty set, then we could have just as well drawn that Venn diagram without overlapping those circles and we would not have lost any information whatsoever. Okay? So in mathematical terms, sets A and B are mutually exclusive if the set A and B is empty, or if the probability of A and B occurring is zero. Okay? So, what are some examples of this? If you roll a die, you get an odd number. Well, you can't also roll an even number. So the event rolling an odd number and rolling an even number are mutually exclusive. You can't do those at the same time. Same thing if you flip a coin, right? You can either flip it heads or you can flip it tails. You can't have a result when you flip a coin that is both heads and tails, right? They are mutually exclusive. So let's take a look at a couple practice problems. Okay, so what is the probability of either rolling an odd value on a die or rolling a value greater than or equal to 4? Now, before we talk about any formulas that we're using or anything like that, let's actually talk about how we're going to approach this, because this is now dealing with a bit of terminology that we haven't explicitly defined or explained. In the past couple weeks, we've been dealing with independent and dependent probabilities, particularly, and that dealt with two sets that are ANDed together, right? What's the probability that you choose a red marble first and a blue marble second, right? We're keying in on that AND key term. And when you use that AND key term, we would multiply those probabilities together. Okay, so whenever you're dealing with A and B, you want to be thinking multiply. However, in this case, we're dealing with an A or B situation, right? An either A, rolling an odd value on a die, or rolling a value greater than or equal to 4. Okay, so A or B. We're dealing with probability of A or B. When we do this, the thing I want you guys to be thinking in the back of your head is addition. I want to add results together. Okay, so let's actually take this first problem apart, probably in more detail than you care to think about, but it's good to explore it. All right, so what I've done here is I've drawn out a Venn diagram of all the results of rolling a single die. Okay, inside our odd circle, I've put the 1, 3, and 5, and inside our greater than or equal to 4 circle, I've put the results of 4, 5, and 6. And with a special note of 5, because it is both odd and greater than or equal to 4, it gets to lie in the intersection here. And then, of course, we can't forget about 2, right? 2's on the die, but it is neither odd nor is it greater than or equal to 4, so it just has to sit out here in no man's land or omega land. Now, the traditional method that we would go about answering this problem is we could identify what parts of our Venn diagram satisfy this set relationship, rolling an odd value or rolling a value greater than or equal to 4. And we could shade that in. And we use a highlighter instead of a dark pen. Okay, we could shade all that in like this. And we could ask ourselves, okay, how many events occur inside that shaded area? Well, there's 1, 2, 3, 4, 5. I have a total of 5 events out of our possible events, or our sample space, of 6, as there's 6 sides on a dice. Okay, so I know just from drawing out a Venn diagram, counting up individual events, and knowing what my sample space size is, that my probability should equal 5, 6. But we just got done saying, hey, whenever you're dealing with the OR keyword, I want you thinking about adding. Well, what are we adding? Well, what we're going to be adding is probabilities or totals of complete sets. Okay, so let's get our pen out. Recall that a while ago we said that there are tools that we can use, formulas that we can use that are going to help us out anytime that individually counting out probabilities is going to get really cumbersome or troublesome. So the example that I believe we were looking at there was with a deck of cards, and anytime you drew a second deck of cards, all of a sudden you're blowing up that sample space really quickly. And especially if you have like 3 or 4 events, you don't want to have to start wading through a million different possible events and then getting out your little tally board and saying, yep, 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 or nope, that didn't match, that didn't match. Okay, you don't want to have to individually count all those things. Same thing is going to apply here. We want to be able to tackle this same type of problem, albeit perhaps with a little bit more difficulty or complexity, without having to resort to Venn diagrams or tables and physically counting our results. Okay, so the way that we want to do this is instead by adding up entire buckets worth. Okay, there might be a million events in this odd circle. Maybe we have a 2 million sided die. I can't fathom rolling one of those things, but maybe it's got 2 million sides and half of them are odd. So you've got all those results. I don't want to sit there and add up a million different results. I could just say, hey, I know that there's a million in the odd group. So let me start off by counting 1 million, right? Plus, however, are in my other bucket, right? If I know that it's a 2 million sided die and I'm looking for the sides that are greater than or equal to 4, well, it's 2 million minus the first 4. The first 3. 1, 2, and 3 kind of don't fit in there. So I would add up, add this to 999,997, right? And hey, now I've got a total of how many dice are in there. But there's a problem. And to do this, let's go back to address that problem. Let's go back to just our simple 6-sided die and see how these results are going to come out. Okay, so let's add up all of the odd dice on just our 6-sided die. I've got 1, 2, 3. That's how many total results I have in here. So in our odd camp, I've got 3 dice, or sorry, 3 results. And in our greater than or equal to 4 circle, we have a 4, 5, and 6. We also have 3 results. Okay. Now, if I add these 2 results together, 3 plus 3 is going to equal 6. And if we divide that by our total sample space of 6, do y'all see the problem here? We've now come up with a different probability than we initially calculated before, just by adding up the individuals. Something's going wrong here. Okay. Now, you might be going, hey, I see what's going on here. You might have already picked up on this. Notice that when I count up all the numbers in the odd circle, there's 1, 2, 3, and all the numbers in the greater than equal to 4, 1, 2, 3, in doing that, where those 2 circles intersect, I have now counted that event twice. Okay, I counted it 1, 2, 3. There was the first time. 1, 2, 3. There was the second time. I've counted that number twice. And so this sum, if I add up the 3 and the 3, that's including 2 copies of this intersection. Okay, now to fix this sum here, we need to subtract away the intersection. So our odds intersects with greater than, not less than, greater than or equal to 4. How many are in that bucket? Well, there's just 1, okay? So if I add up those 2 and subtract this one, this is now going to give us 5 over 6. Okay? And this leads us to our general problem for solving for the probability of 2 events, the union of 2 events. A, remember this union symbol kind of stands for or. The probability of A or B occurring is equal to the probability of A occurring. What was that? Well, in this case, it was 3 over 6. All right, 3 out of the total 6. Do note that these are saying probabilities, okay? It's not always necessary that everything has the same sample space, so you can't just add up events without having common denominators and whatnot. So this is a very simple example, but in our general formula, we're actually going to calculate the probability of this occurring, the probability of this occurring, and the probability of this occurring, and then doing our addition and subtraction. So the probability of B occurring was, again, 3 out of 6, minus the probability that the intersection occurred, which was 1 out of 6. So if I do 3/6 plus 3/6, that's 6 out of 6. That was our initial result. Minus the 1/6, that's our corrected result of 5/6. This is going to give us our 5/6 result. Okay. So this is critically important. This part where we correct the sum, this is critically important because these 2 events are inclusive. Okay, when they're inclusive, you are always going to have some term in that intersection that gets counted twice. Okay, that was our definition of inclusive. That intersection is non-empty. So when I'm adding up these 2 sets combined, there's an extra copy of that intersection. All right, now let's look at a scenario that is now mutually exclusive. What is the probability of either drawing a lettered card or drawing an even-numbered card? Okay, so in this one, I've let A be our even-numbered cards, and if we look at our little grid here, I know that this is an even, that's even, that's even, that's even, that's even. So I've got 1, 2, 3, 4, 5 cards in each suit, and I've got 4 suits, so that gives me a total, 5 times 4, of 20 cards that are even numbered. Okay, but it's also important to note, because we have to take into account this intersection to figure out where, how much gets split in between. It's impossible for me to draw a lettered card, okay, or a card that has a letter in the corner, if I've drawn a card that has a number in the corner, right? These are even numbered cards. There is no intersection here. I don't know why my mouse skipped there. There is no intersection here. So this 20 is going to be even numbered cards that are not lettered cards. Okay, so I can put the 20 over here. Likewise, if we count up our our lettered cards, there's one, there's one, there's one, and there's one, right? Ace, even though sometimes we think of this as having a value of 1, it does still have a letter in the corner, so it's considered a lettered card. So we've got 1, 2, 3, 4 lettered cards in each suit and 4 suits. That gives a total, 4 times 4, of 16. Okay, and again, each of those cards cannot also be in an even numbered card. They're not numbered, let alone even. Okay, so this 16 is going to sit over here. And last but not least, we've got our odd cards, our odd numbered cards. Okay, and that's going to leave us with 16 out here in Omega Land, in No Man's Land. And now we can use the exact same formula as before. Okay, what's the probability of A occurring? Well, A was our even numbered cards. There's a total of 20 in here. So a total of 20 out of 52 cards in a standard deck of cards. Plus, what's the probability of B occurring? Again, that's 16, right? 0 plus 16, or NB. 16 over 52. Okay. Minus the intersection. Well, our intersection is 0, right, where those two circles overlap over 52. This will give us a result of 36 over 52. And I'll leave you guys to go ahead and simplify that on your own to see what that simplifies to, or if you want to turn that into a percentage. The important thing that I want to point out here is whether or not these were mutually exclusive or inclusive events, we've used the same formula, okay? And so that might beg the question, well, why do we care about whether or not it's an inclusive or mutually exclusive event if we're using the exact same formula for both? And that's just so if you wanted to, you could use a shortcut. Okay, now what's the shortcut? Well, because these two events are mutually exclusive, I know that this intersection where those two circles overlap has to be 0. It's empty. Okay, has to be 0. It's empty. That means that this probability down here, the subtracting or the correcting part of our equation, it also has to be 0. Right? There's 0 out of however many total sample space there is. It's always going to equal 0. And so in effect, if it's mutually exclusive, I could take a shortcut and not have to deal with these two things, okay? Now, another thing that we could tackle is perhaps I don't know what all the different events are or how they're laid out or anything like that, but I do know, say, the probability of A union B, or A or B occurring, and I also know the probabilities of A and the probabilities of B occurring, okay? We can then determine whether or not A and B are in fact mutually exclusive, whether they can happen simultaneously just by comparing the sum of the probability of A and the probability of B and seeing if it equals the probability of A or B, okay? If this sum of these two terms is not equal to this other term, the A or B, then I know I have to have been subtracting some corrective term in order to get this one, okay? And that tells me that, yeah, there's a relationship somewhere in there. There's an overlap. And just how far apart these two sums are can kind of tell you how related they are, right? How intertwined or inclusive they are from one another. Right? If there's only one event out of 52, right, this corrective event is going to be very small. And so these two numbers are going to be very close to one another. However, if a whole lot of A overlaps with a whole lot of B, and there's 50 out of the 52 cards that match this criteria, well, all of a sudden, this result over here and this result over there, they're going to be wildly different, okay? And so this equation can tell you whether or not things are mutually exclusive, Okay, so that's an answer or a question you could answer given these probabilities. And you could figure out just how inclusive they are. Now, another thing that can be solved here, if you'll pay attention, right on this right-hand side, out of this entire equation, I've got four different terms: probability of A or B, probability of A, probability of B, and the probability of A and B. Okay, four different numbers in there. If I have three of them, any three of these, right, I can substitute those values in and solve for the fourth. Obviously, we might have to do some simple algebra to move numbers across the equal sign, but we can set that all by itself and solve for it. So maybe I know the probability that A occurs, and I know that probability of A or B occurs, and I know the probability that A and B occurs, but I don't know what the probability of B is. Well, we can plug those values into this equation and solve for what's the probability of B occurring all by itself, right? Even though all the premise has been largely centered around the probability of A occurring, because we've been given this intersection and ORing pairing here, we can then back into what the probability of B is. Okay, so this is a fairly powerful, albeit simple formula that can actually tell you quite a bit about the probabilities of two events. So again, just as a quick rehash, going back a couple weeks, anytime you're dealing with probability of an A and B occurring, we want to be thinking in our minds multiplication, right? What's the probability of A occurring? What's the probability of B occurring? Multiply them together, okay? When we're dealing with OR, like is the case here, what's the probability of A or B, or the union, okay? I want to be thinking about adding terms together, with the caveat that we probably have to correct it by subtracting some extra copies. But in general, I want you to be thinking multiply is and, adding and subtracting is or. Okay, that's going to let you deal with some more complex situations than really what we've been covering in here. But as long as you remember that and you remember these formulas, you should be set to go. So this should cover all the tools you need to handle the worksheet that I've assigned to you this week. Again, if you have any questions, please feel free to reach out. You can reach me by email, or you can join a Zoom meeting. We can have a one-on-one conversation there. And with that, I hope you guys stay safe. I hope you guys stay healthy, and we'll talk to you later.